One of the two semi-plenary presentations today is given by Zhou Jin from the City University of Hong Kong, China. The presentation is followed by a live panel discussion, including selected experts on the topic. The session is chaired by Rolf Findeisen from the University of Magdeburg, who will now introduce the speaker.
It is my great pleasure to introduce the semi-plenary speaker Zhou Jin from the City University of Hong Kong. My name is Rolf Findeisen from the Otto von Guericke University in Magdeburg, Germany. Let me also welcome you as the IPC co-chair of this Ifac World Congress. I hope that you will enjoy this exciting semi-plenary talk, as well as the whole Ifac World Congress in its virtual form. Zhou's and my paths crossed first more than 23 years ago. At that time I was an exchange student at the University of Wisconsin-Madison, and Zhou, a young faculty member at UT Texas in Austin. Since then our paths have crossed many times at many meetings, conferences, workshops and other events. I am excited that we could convince Zhou to give this semi-plenary talk and to share some of his insights into industrial intelligence based on systems and data view. Let me tell you a little bit about Zhou and his career. Zhou obtained his bachelor and master degree in automatic control from Tsinghua University. He then joined the chemical engineering department of the University of Maryland, from which he received his PhD. Before his current appointment as the Dean of the School of Data Science and the Director of the Hong Kong Institute of Data Science at the City University of Hong Kong, he was a professor at the University of Southern California and UT Texas in Austin. Zhou is an internationally very well-known scientist. He received many awards and recognitions, which would take much too long to be presented here. He is a fellow of Ifac, IEEE and AICG. He served on many editorial boards, and his work, focusing on data analytics, machine learning, process monitoring, fault diagnosis and model predictive control, are widely visible and have influenced many researchers worldwide. So let me hand over the virtual floor to Zhou to provide insights into an integrated framework of systems, data and industrial intelligence towards Industry 4.0.
I would like to thank Mr. Chairman for the introduction, and also thank the president of Ifac, Frank Algover, invite me to give this talk. I think the topic is about integrated framework of systems, data, and industrial intelligence towards Industry 4.0. This is a quite big topic, but I'll try to give a little aspect of this big topic. I'm Zhou Jin. I'm a chair professor at the School of Data Science. I want to mention a little bit about the school. It's a fairly new school. It has a focus on data science, but it has systems behind the data that we're analyzing. So the outline of the talk is like this. First, I'll just talk about how machine learning can help to achieve the Industry 4.0. And then I'll talk about some specific issues that we've been working on. We know about 4 years ago, this AlphaGo was a big event that brought the power of AI or machine learning to the game of Go. And basically it beats the world champion with a 4-to-1 ratio. That's a landslide winning. That was one of the events that sort of showed the public how machine learning can really attack on very complex problems. And then about a year later, this founder of this Google's DeepMind, Demis Hassabis, presented another talk. It's called AlphaZero. What it is actually a new version of AlphaGo that didn't learn from actual data. It actually learned from computer-to-computer simulation, and it only took about 3 days of simulated games for the machine learning to pick up how to beat even the best master of Go that they developed earlier. So the two events or the two experiments really showed us something about AI. One is why it's so powerful to beat the human best player. And the other thing is why it didn't need data to beat the best Go game around. So coming towards this Industry 4.0, we can see that there's a big interest and moving towards the next industrial revolution. There are, of course, multiple technologies that has to work together to make this happen, but definitely big data, industrial Internet of Things, and other powerful computing and communication technologies have to work together. So what we're looking for is for this Industry 4.0 to propel breakthrough improvements in safety, reliability, and also productivity. And they will also want to derive intelligent decision making using data analytics and artificial intelligence. The question is whether the power that beat the human best Go player could be directly translated into Industry 4.0. The question is actually is questionable because the games are not the reality. For games like Go, basically the models are perfect. The white boxes, disturbances or the opponent's moves are 100% measurable. And then the rules are perfectly clear and the objective functions are known and fixed. Finally, the whole system is time invariant. So between the player or the controller and the opponent or disturbances, it's entirely symmetric. It's 100% wide. Now for industrial systems data, this is not the case. We do have a lot of known principles and simulation models. The simulation models are good for well-understood processes with known parameters, such as well-designed machines. And also they are for usually normal operations and known fault scenarios. And then for the fault scenarios, cannot be completely exhausted. On the other hand, process data are good for situational knowledge. The data reflects real-time situations, and data encompass all uncertainties and faults. And therefore, unmodeled disturbances and faults show up in the data. So one message I would like to bring up now is basically in order for machine intelligence or AI to work for Industry 4.0, we need to consider both model and data together. The paradigm should include both of them. And when an anomaly situation happens, it's unrealistic to expect the models are still correct. And data will provide situational knowledge of operations with the help of proper data analytics. And increasingly, the model and data should work together for smart operations, and models for expected situations and data for unexpected situations. Another message I want to bring is for industrial intelligence, we need to make them human-centered. Human needs to be in the center of the whole cyber-physical system to form the cyber-physical human system. And these are the three elements. Just between cyber systems and also the physical processes, there are data and models that can talk to each other. However, the human operator needs to make decisions, or the engineers needs to make decisions. It will interact with the cyber physical system through data analytics. It also would interact directly with the physical processes when something abnormally happens. You could intervene the system or provide manual override. This is the second message where the human
decision maker needs to be involved. There is this bad accident by the 737 MAX we all know about. There were 2 bad accidents. The problem was basically the designed subphysical system did not have the pilot involved. Now, for process data analytics, which is one important scheme to derive intelligence from data, this is our next topic. First, we have to review what is a process. I get this simple statement from my colleague, Alain Ben-Susan. This is a very important way to characterize what a process is. Basically, a process is a system that evolves in an environment. Therefore, it has a system and also the environment around it. Therefore, for process data analytics, we need to analyze data from both the system and the environment. There are 3 attributes for process data analytics to work. It needs to work with the first principles models. It also needs to learn uncertainty from data, and also it has to generate interpretable solutions in a way that it'll have the human operator's confidence. And also, the human operator will be finally responsible for any abnormal situations or any bad situations that might happen. The third message I want to bring about is data can help us see the dark side, which is the uncertainty. Data analytics are going to help us derive the insight behind the data, but the challenge is how to learn this and also how to interpret the uncertainties. Hopefully the right machine learning tools will lead us to that. So this cartoon will basically say that with the proper analytics, we can make the dark side visible or interpretable. Now, the next block of material will be focusing on process data analytics. Now, the AI resurgence today, they are basically application driven. We know that there are a number of very successful applications like image analysis and natural language processing, and to some extent, autonomous systems. So we're going to talk about Industry 4.0 for the interest of this talk. There are 3 uses of process data analytics. These are the 3 most important uses. They're either for prediction purpose, like inferential sensors, or for interpretation, like visualization by dimension reduction, and for diagnostics. And finally, they could be used for decision making. So data analytics or modeling are not just for the most accurate prediction, but it's also for interpretation purpose and decision making. I'll give several examples. One is in the modern day of industrial IoT, we'll have many sensors installed on a process. And the dimension can be very high, but the actual dynamics could be low dimensions. This is another industrial process. That's a paper machine. It's making paper. And on the right side, there is a fault that's about to happen. You can see there are a lot of the data that's showing strange signatures before paper shade break happens. So what is the features behind this data that we can extract to understand shade break is about to happen? That'll help us avoid it. Another process is this chemical process, which actually shows quite a bit oscillations in normal operations, and it's hard to know what's happening. So in the analytics side, we have understood that these recycle loops can bring bring in these snowball effects, which basically amplifies very small abnormality and to make them big ones plant-wide. And the data recorded from this process was studied by Nina Thornhill and other researchers in the past, and this is what they look like. They're all over the place, oscillations in almost every variable, but it's difficult to know where they're coming from originally. So for this data series, are there any interest, or what are the interest to analyze them? I quote these 3 points from the econometrician, Professor Tsay. Basically, on econometric side, they do analysis, and their reasons for doing them could be very similar to ours. One is to predict important quantities, like state and unemployment rate. Another is to find the relationships of interest, both spatial and temporal. Third one is to search for common features among the data. I think these 3 reasons spoke very well about what we are looking for process data analytics. Now for PDA and monitoring, there has been a lot of research doing process monitoring for a controlled process system like this with multi-level controllers. For unsupervised monitoring, we collect process data from all DCS and other computer systems, and then analyze the data correlation to provide monitoring of abnormal situations using tools like principal component analysis. There are also concerns about quality, actually more importantly, with quality data that might come with a delay because of the lab measurements and other indirect measurements. We have interest to monitor what faults are actually causing quality deviations, and also we can infer the quality predictions to know what might happen before the actual analysis results are available. So this scheme with both process data and quality label data together is known as supervised monitoring. So I'll first focus on unsupervised monitoring and data analytics. So for this process data, they are actually dominated by time series data. They are serially correlated, and they are also cross-correlated, especially with IIoT. There's high collinearity behind them. And we also have enlarged scope of measured data that makes them high dimension. And then there is multi-level, multi-source data that could be irregularly sampled, and their image data it basically forms the high mix. Now, the audience might be familiar with the system identification, so I'm comparing PDA with the system ID. You could look at the right side while I'm talking about the left-hand side. Process data analytics are looking at operational multi-source data instead of designed experimental data. The data are highly collinear, not fully excited. They are partially dynamic, so they're not full-dimensional dynamic. And the purposes or the aims are for extracting features and to be used for monitoring or inference, for fault diagnosis, for interpretation, and also for prediction. So this is my number 4 message. And to do data analytics well, we need to integrate systems theory. That's my number 4 message. Now, let's look at the dynamic latent variable problem and solutions next. Let's say we have measured data on the right-hand side with 5 measurements sensors. However, the driving force behind the 5 are actually 3 factors. So these are the 3 factors, with 1 being dynamic, the other 2 being static, which means they're not serially correlated. So there is a mix happening to show up in the 5 measured data. So the latent variables can be characterized whether they are dynamic or not. If none of them is dynamic, and then this is simple, it's a basically static problem. We can do PCA to analyze them. If they are entirely dynamic, then the standard Varma or state space modeling would work. However, if they are mixed, which means part of them are static, part of them are dynamic, and the dynamic dimension is reduced relative to the measurement dimension. This is the new topic we're talking about today. That's dynamic latent variable methods. How do we do it? Basically, how do we extract the most dynamic components from 5 measured data series? One idea is to do PCA first of the 5, and then look at the 3 principal components and model the components with AR models. This will not work because PCA maximize variance only, and you'll leave a little bit of dynamics everywhere. The other idea is to do a vectored AR model of the 5 first, and then using PCA to model the residuals. This is what's done by Box until about 30 years ago, 40 years ago. The drawback is it's a 4-dimensional solution, and therefore it's sensitive to collinearity in the data. So for latent variable modeling, we're doing this. We have to first do a model dimension reduction. We try to combine the original dimension data into a few components like this, one dimension. And then we make this one component to satisfy some criteria. For this case, we want to make them most predictable. Let's say the solution exists because there exist the most predictable measurements out of 5. Then by combining all 5 with optimal weights, it is possible to make the combined variable to be more predictable than any one alone. So we have one that could be most predictable if we do the right combinations. Now, for the purpose of dynamic latent variable analytics, it is to handle serial correlation as well as cross correlations. So it's desirable to extract the dynamic latent variable for visualization and interpretation purposes, and also to avoid collinearity and to make predictions and also make statistical inference for monitoring. Now, dimension reduction and latent variables goes hand in hand. Now let's formally form the framework of this dynamic latent variable problem as follows. The linear combination of the original measurement vector will give us one latent variable. And then we want to find this linear combination vector R. If the combination leads to a latent variable that's serially uncorrelated, this is known as a static latent variable. If it's serially correlated, it is a dynamic latent variable. So the dynamic latent variable can be expressed in this following state space form. We have 3 vectors. And the first one is the state vector Z. T is the latent variable or dynamic latent variable extracted from data. And then the data vector is X. There is this requirement is that the latent variable dimension is smaller than the measurement vector dimension. Now, one thing to mention is that the DLVs are not the same as state variables. For example, in this one, we have the latent variables in this 3rd order AR form, which would require 3 states to characterize this dynamics. And now there is only one latent variable. There are two measurements. Therefore, the latent variables are not the state variables. Now, for one of the latent variables I, we can have a common filter formulation to make its predictions. So that's the combined data. If we knew the R, we would be able to find a combined series. This series will generate its prediction through this common filter expression, and the corresponding Z state will be the observable states. Now, this expression for the prediction has also an equivalent AR expression like this. And that's a standard operation, and let's denote all the Markov parameters as beta. So since the A matrix here is always stable in common filter formulation, we can truncate the high order model into up to order S. Therefore, what's beyond S will be negligible. We have this expression now. You can see the prediction of the latent variable T hat is parameterized with a bilinear term. One is the beta, that's the dynamic part. The other one is the R, which is the linear combination of the original variables to give the latent variable. Now, how to formulate the objective to be most predictable? This is the objective. For the ith components we try to formulate, we want it to be most correlated with its prediction. And also we want the new component to be uncorrelated with the previous components. Therefore, they have mutual independence in a way. There are two ways to enforce constraints. One is to do it like PCA, so we call it DIPCA. We'll just restrict the weight vector to be norm 1, and also the dynamic combination vector to be norm 1. And the other way is to enforce the variance of the extracted component and the variance of the predictions to be 1. And this will definitely give us the correlation information, and this is the dynamic canonical correlation. So for this dynamic LB approach, we do extract these components one after another, and that's required in order to achieve a mutual orthogonality there. Numerically or computationally, we do it by the sample statistics. So that's the correlational covariance between the extracted latent vector of data and the predicted vector of data. And then with these constraints, if we change the constraints to this set, it'll be the dynamic, I'm sorry, this is the DICCA, dynamic canonical correlation. Now, the solution for DIPCA is given as an example. We can apply a Lagrange multiplier to the objective and constraints to get the solution for beta and gamma. You can see they are not easily solvable because to find W, we need to know beta. And this W seems to be like an eigenvector of this very complex matrix. Now, to find beta, we need W. And so these two equations are interacting, then we'll have to solve them iteratively. The good news is after the solution is solved, the DLVs are almost predictable, actually in descending order. And also the dynamic latent variables are mutually orthogonal because we enforce them to be orthogonal. And for the original data like this, we basically expanded in terms of its orthogonal basis, which each of them is a time series, and they are mutually orthogonal. And this is the loading matrix. Now, let's take a look at how do we use the DLV as feature analysis and also for monitoring. I'm going back to this example. This is a real process with a lot of data that shows oscillations. We want to analyze this data, and one demonstration is this. By feeding this set of data to dynamic CCA, we get these are the extracted dynamic latent variables in descending order. So you can see their dynamics are decreasing. However, there's also another feature that there seems to be low frequency dynamics are extracted first and then followed by increased frequency latent variables. If we take one of them and then look at their corresponding weights, this is one of the components. It looks like it's mostly focused on 3 variables, and then we can dig into the corresponding 3 variables to see what they are. And you can see the first one is really heavily loaded towards the extracted latent variable, and the second one is somewhat loaded, and then the third one is actually pulled in to cancel the not needed high frequency loss oscillations from this particular latent variable. So the procedure for analyzing features or troubleshooting the data is like this. So we start from the process with a somewhat process understanding. Then we collect data from the process, and we feed the data to this dynamic CCA analytics to get the latent variables. And then we can check the interesting features out of these latent variables. And for the interesting ones, we do look at the weights or the contributions and find the potential causes, and then fix the problems. And then we hope to improve the operation of the process by fixing the potential problems. So that's how we can use the extracted dynamic latent features for process troubleshooting and improvement. Now, the other use of these dynamic latent variables is for process monitoring. Now, this is beyond the principal component-based monitoring. For the dynamic latent variable process, we can have equivalent innovation forms like this. Basically, the latent vector can be reduced to its innovations based on the dynamics. And this important message here for monitoring is that to monitor these dynamic latent variables, we need to look at the conditioned covariance, which means based on the data we already know, what's the unknown part that forms the covariance of the latent vector. And therefore, the conditional covariance should be monitored rather than the unconditional covariance. Okay, and the conditional covariance of the latent vector is actually the covariance of the innovations, and that's the big difference there. I want to show an illustration using the Tennessee-Eastman simulation data. This big ellipse is what you would get if you don't do the prediction, if you don't do the conditional covariance. This is unconditional covariance that will define the control region. You can see it's very big. Now, with the prediction involved, we can do the unconditional, we can do the conditional monitoring. That will give us this smaller ellipse to define what is normal. It basically will move with the prediction, and then around the prediction there is uncertainty. If the new data point is within that uncertainty is considered normal. We can collapse all these small ellipses down to there. So it's well-defined control region, and it's much smaller control region. Now, in practical use, the unconditional monitoring would define a very large region, but this conditional or predicted monitoring will do much tighter control. Now, let's look at the supervised monitoring part and also prediction. So for the problem of process data analytics, we do have this, in some cases, we have label data or quality data, and then we need to understand what is the connection between process data and the quality data. Therefore, when something happens on the quality data, we can predict it using process data. Now, to make a brief discussion, this is how it works. Basically, we can form the same kind of dynamic latent structure on the X side. However, the objective is to drive the latent variables to predict another set of data Y as best as possible. And there are two objectives one can formulate. The dynamic PLS is similar to the partially square objective, which is maximizing the covariance. And then the dynamic latent vector regression is another modified objective. So I just provide a reference here for those who are interested. For the latent variable analytics, there are definitely related work in other domains. I'm highlighting this related work just for comparison. In the machine learning and other domains, there are a lot of research going on studying forecastable component analysis and also predictable feature analysis. These two methods or two categories of methods are very closely related to our dynamic latent variable methods. And there's also a lot of study in econometrics on dynamic factor modeling with a little bit different interest and different set of problems. What we're familiar with is actually subspace identification. That's for the purpose of building a good model for control. And to extend all these methods to nonlinear approaches, it's actually straightforward to use kernel methods or kernelization to develop all the nonlinear extensions. Now, I'd like to make just one point is that subspace identification, such as canonical variate analysis, does not extract latent variable or dynamic latent variable. The issue is this. For subspace identification or CVA, they extend the future, the measurement data vector to the future for a window of size f. So they do this such that so that they can introduce the observability matrix that can be related to the state vector sufficiently. So what it ends up with is extended future measurement vector as a sort of latent vector model in terms of the state vector, not the original latent vector. And the rank of this matrix is going to be increased. Instead of P, it's going to increase to the rank of the state vector dimension. And therefore, to model this extended observability matrix, we only get the state variables, Z, not the latent variables, T. Now, having analyzed all of this, we can see that analytics can differ a lot in three aspects, at least three aspects. One is a model structure, whether the model has appropriate structure. That's one important thing for characterizing dynamic latent variables. The second one is actually parameterization. We need to have parsimonious parameterization to achieve dimension reduction. The very original effort by Box and Till, they didn't do dimension reduction. They use full dimensional vector AR. Therefore, in their computation, they're not doing dimension reduction. Now, a lot of methods actually doing dimension reduction of latent variable just for the response side. Basically, in the objective, the response side has dimension reduction, but the predictor side is full space. So the most parsimonious representation is actually to have dynamic latent variables in both response and the predictor side. And this is very important. And the third one is what objective function we're using along with the constraints. By changing the constraints, we can see the results can be very different. Now, I just want to say that to compare different analytic methods, we need to look at all these three aspects. Now, I'd like to conclude this talk. First, process data analytics are at their best time in recent decades. We define process as a system evolving in an environment. And also, we basically say all data ought to be useful. This is like the big data spirit. And then data analytics can bring intelligence and insights for decision making. And then system theory has an important role to play in process data analytics. I'd like to acknowledge my former students and collaborators, Dr. Yining Dong, Dr. Qinqin Zhu, Dr. Gang Li, and Professor Jin Wang, and also Professor Qiang Liu. I'd like to acknowledge the Center for Systems Informatics Engineering at CTU and the Texas, Wisconsin, California Control Consortium. With that, conclude my talk. I want to thank you for your attention.
And then smart cities and Industry 4.0 is another area. I think Hong Kong is one of the cities I would call it pretty smart, especially the transportation, how people move around. So I would say in the future, we'll get smarter because we have a lot more things being censored, and with the Internet of Things happening, we'll get a lot smarter, a lot more efficient. The Industry 4.0 is basically the fourth industrial revolution. In this case, it's actually digital revolution with machine learning or data science behind it.